Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series for the BSc Honours Physics students. We have been going through the section on optics, and in the lecture which will be delivered today, a part of it will be belonging to the wave optics. The rest of the things will belong to the section on interferometry. So, the contents of the lecture 21 will be as follows. 1. Determination of refractive index of a liquid by Newton's rings. Number 2. Haidinger fringes. Introduction to interferometry, Michelson Interferometer, and construction. In continuation to what we have been doing in the last lecture, I told you about the Newton's rings experimental setup and as to how it can be used to evaluate the wavelength of a monochromatic source. Not only determination of wavelength of the monochromatic source, it can also be used to determine the refractive index of a liquid. That is what I told you in the last lecture. The expression which will be exactly used will be given by the equation that you have got here. dp prime square will be 4p multiplied by r into lambda by n. As I told you, n will come in the denominator, and as n will have a value higher than 1, for water it is 1.331, for glass it is 1.5, the refractive index of the denser medium will be greater than 1, as a result of which the diameters of the rings will be shrunk, will be lesser than the diameter that you will be getting in the case of air. Therefore, the refractive index works out to be an expression of this kind: dm square minus dp square, the diameter squares of the mth and pth rings respectively, and then the same thing comes to them, similar expression comes to the denominator. That gives them refractive index of a liquid. This is a continuation of what I did in the last lecture, and now we move on to the formation of what we call as Haidinger fringes. As again I told you in the last lecture, in the case of Haidinger fringes, we have got a extended source. You have got a light source here, and the light coming from the source makes an angle of inclination I here, right? You have got I is the angle that you have here, the same I is here, and so the light coming from this will be incident on thick glass plate or thick film. You have got a film here, you have seen the air wedge. Similarly, you have got a film here, and the light rays are incident at the points A and B, and the light rays which go through the points A as well as B will undergo reflection at the bottom plane, and they will emerge and go through the convex lens, leading to finally the points A prime and B prime. So, the two rays that you are talking about here, one ray coming from the top surface and the second ray which undergoes reflection at the bottom surface comes here. These two rays will interfere. The rays are interfering as in the case of Newton's rings or in the case of air wedge. Obviously, in every cases you will be having one ray coming from reflection suffered by the light ray at a particular surface, the other passing through either air film or you got a film from the bottom surface. There are two surfaces, so partly the light ray will be reflected at a point A and a part of it will undergo transmission and it will suffer reflection at this point. There is extra path difference, right? That depending upon the extra path difference, then the point A prime that you eventually get will be either bright or dark, and around this A prime B prime you will be getting a circular ring. As I told you in the last lecture, the intensity of the ring will be much lesser than what you will be getting in the case of Newton's rings. To improve the intensity of these rings, you are making use of a lens, and therefore you have, if the thickness of the film is large, the path difference will change considerably even when R changes by a small value. Fringes are produced in this case are due to the superposition of rays. As I told you, the two reflected rays, they interfere or are getting superimposed, which are equally inclined to the normal. Because they have the same inclination, these fringes are called fringes of equal inclination. The fringes of equal inclination are known as Haidinger fringes. In this case, all the pairs of interfering rays of equal inclination pass through the plate as a parallel beam and hence meet at infinity, because parallel rays will meet at infinity. The other points of different inclination will meet at different points at infinity. Therefore, they can be located with a telescope focused to infinity. The fringes are therefore said to be localized at infinity. To produce Haidinger fringes, number one, the source must be an extended source with monochromatic wavelength. The film thickness must be appreciably large. The observing instrument is to be focused for parallel rays. So, there are things to be met, the conditions to be met for obtaining the Haidinger fringes. So, you should have a monochromatic source, that is what you have here. Then it should be extended source, as I told you just now. The film thickness, as I mentioned to you earlier, should be larger compared to what we had in the case of Newton's rings or air wedge. So, a lens is arranged parallel to the plate and a screen is kept in the focal plane of the lens. Light from the extended source is incident on the plate in diverse directions. The waves propagating parallel to the plane and falling on the plate at an angle I at points A and B. You see the points A and B, right? The points A and B. Points A and B get reflected from the top and bottom surfaces of the plate, as you have in the case of air wedge or Newton's rings. In both cases, there will be two reflections taking place, one at each surface. Here is the top surface, the other one is the bottom surface. These two rays will be interfering, and I will be now showing you the conditions which are to be satisfied by these two rays which are coming here. When they interfere, what are the conditions under which there will be constructive or destructive interference. The waves incident on the top surface of the plate at an angle I travel along the generators of a cone. Each parallel reflected waves interfere at diametrically opposite points. You know the points A prime and B prime. Thus, a circular ring is produced. Something like in Newton's rings case, a circular ring is produced. Similarly, the waves incident at a different angle will produce a collection of identical points arranged along a circle of another radius, and so you will have concentric rings, as we had in the case of neutron strings. You have the constructive interference taking place at A prime, B prime, and that will lead to a circular ring, and similarly there will be other rings with different diameters. As a result, a system of alternating bright and dark circular rings with a common center will be observed on the screen. Now, let me go to the conditions. You all know by now what we understand by constructive interference and similarly destructive interference. So, each ring is characterized by a particular value of n. So, you talk of the order of the ring, nth order. So, the condition for bright rings are, the bright rings are produced when the condition 2 mu t cos r is equal to n lambda. What are mu and t? Mu is the refractive index of the medium through which the rays 1 and 2 are separated. You know, one ray will be suffering a reflection on the top surface, the other will travel through a film, it may be air or some liquid, and getting reflected from the bottom or the top surface of the glass plate, or whatever be the bottom or top surface. So, the two rays will be there, they will be interfering, separated by a medium. The medium, as you know, it may be air or water. So, mu is the refractive index of medium, and T, what is T? T is the thickness of the film thickness, right? T is the thickness of the film, and the cos r, you know, the angle r. N is the order of the ring, as I told you. Lambda is the wavelength of the monochromatic source. Having said this is the condition for constructive interference, by now you will be knowing the condition for destructive interference. Can you tell me what is the condition for destructive interference? Instead of n lambda, it should be having n plus 1 into lambda by 2 or 2n plus 1 into lambda by 2. Okay. When n is 0, what will happen? The right hand side will become lambda by 2. So, when n is 1, 2 plus 1, 3 lambda by 2. N is 2, it is 5 lambda by 2. Therefore, whenever the path difference. Now, what is 2 mu t cos r? That is the path difference, right? The condition for dark rings are 2 mu t cos r to be equal to 2n plus 1 into lambda by 2. Therefore, whenever the path difference is lambda by 2, 3 lambda by 2, 5 lambda by 2, then that is the condition that will lead to a dark point or a dark ring. For a bright ring, it will be, the path difference will be 0 or lambda or 2 lambda. What is lambda or 2 lambda? It is one full wave. 2 lambda means 2 full waves. The path difference will be containing either one full wave or 2 full waves. The parallel pairs of reflected rays meet only at infinity. Therefore, a lens is used to focus them. Accordingly, these fringes of equal inclination are said to be localized at infinity. So, with this we come to the end of the section on wave optics. What is it we have been trying to understand in wave optics? In wave optics, we have been talking about coherent sources. We have been talking about the phenomenon of interference. As all of you know by now, the phenomenon of interference is nothing but two light waves interfering with each other, and the two light waves which are interfering will lead to a stable interference pattern. What do you mean by interference pattern? A dark band, bright band, dark band. The occurrence of alternate dark and bright bands, they are called the interference bands. If you want to have a stable interference pattern, then the two sources which emit light and they lead to interference should be coherent sources. The two sources should be coherent. What do you mean by coherent sources? The lights coming from the sources S1 and S2 should be of the same wavelength, should be having the same phase difference and so on, right? You know by now the definition of coherent sources and so on. So, we have been trying to use the phenomenon of interference, and then we talked about the air wedge experiment and the Newton's rings experiment, and all these things we made use of to determine what? The wavelength of the given monochromatic source. The wavelength of the source cannot be easily determined in a laboratory. Therefore, the wavelength of the light source can be determined as well as the refractive index of the medium. Let us have a break at this point. Welcome back at the break. As I mentioned just now, we have completed the wave optics. We pass on to the new section on interferometry. What is an interferometer? The design and use of optical interferometers. Optical interferometers based on both two beam interference or multiple beam interference of light are extremely powerful tools for metrology and spectroscopy. What is metrology? Metrology is measurement and spectroscopy. A wide variety of measurements can be performed, ranging from determining the shape of a surface to what accuracy? To an accuracy of less than millionth of an inch. The waviness or 25, we are in the nano regime now. We talk of nanotechnology. So, a difference in the depth profile, surface profile, 25 nanometer difference can be determined using an optical interferometer. A difference of the millionth of an inch, the accuracy in the surface measurement, the surface topography. So, the 25 nanometers is a very minute thing that can be, so you can go to a difference of 25 nanometers to determine the separation, and also by millions of kilometers, the two stars separated by millions of kilometers away from where we are, the distance separating the two stars can also be determined using optical interferometers. One is minute thickness variations can be determined, that is the metrology, and also the measurement of the distance separating the two light emitting stars can also be determined using optical interferometers. And not only that, we have got so many other things to be talked about. I will come to those things a little later. So, the credit goes to Michelson. So, Michelson's interferometer, the robust picture is shown on the left side. So, here is Michelson, who lived between 1852 to 1931. Now, what do we know about Michelson? The most important thing is the Michelson-Morley negative result experiment. What do you mean by, have you heard of Michelson-Morley negative result experiment? What do you call negative result? The result showed that there is no ether. Negative result showed, negative result means what? They were searching for the presence of ether. Why do you need ether? Because those people, the proponents of wave theory of light, they assumed that if light were to propagate in space, you require a medium. For light to be transmitted from one point to another point, can you have the sound wave to be transmitted in vacuum? If there is no air here, the sound cannot propagate from one point to another point. I will be moving my lips, nothing will be heard by the listener if the room is void of air. Air is a medium which takes the sound waves from one point to the other point, from the speaker to the listener. Similarly, those who propounded the wave theory of light, the proponents of the wave theory of light, they said light, if it were to be propagated from one point to another point, a medium is required they assumed all pervading ether. All pervading ether means what? In the whole universe is made up of a medium called ether, and the ether medium is a must for the propagation of light. Otherwise, light will not be propagated from one point to another point. If light were to go from one point to another point, it goes through a medium called ether, and they were searching for the ether medium. And the experiment performed by Michelson Morley using the Michelson Interferometer, it showed a null effect. That is the reason why it is called a negative result experiment. It showed conclusively there is no medium like ether. The medium ether does not exist in the universe. That made Einstein to propose the special theory of relativity. The theory of relativity given by Einstein came from the experiment of Michelson Morley. So, the Michelson interferometer is of immense importance from the point of view that the Michelson Morley experiment showed conclusively there is no medium like ether, which was required by the people who proposed the wave theory of light. The wave theory of light is right, but the medium, the ether medium is not there. They assumed the ether medium to be present for the light wave to travel from one point to another point. For the propagation of light, a medium is required. That is what they thought. They assumed ether to be the medium, but such a medium is not present. That was shown by the Michelson Morley experiment. That is the reason why it is called negative result experiment. It is a famous experiment which made Einstein to propose the special theory of relativity, which does not require any medium. Okay. What is an interferometer? An interferometer works on the principle of superposition. Superposition means the word interference. Interferometer comes from interference. There should be two waves which should be interfering with each other. So, Michelson designed an interferometer to determine the wavelength of light. As I told you, you don't get the wavelength of light alone. Apart from that, so many other byproducts are there. That is the Michelson Morley experiment. The basic building blocks of the interferometer that are built by Michelson are a monochromatic source which emits light waves, a detector, two mirrors. Detector may be a telescope, two mirrors, and one semi-transparent mirror often called beam splitter. Michelson interferometer is based on division of amplitude. The light beam is partly transmitted and partly reflected. Light from an extended source S is inclined on a partially reflecting plate. The light is incident on a partially reflecting plate. Partially reflecting plate means what? It will partially transmit, partially reflect. I will show them the instrument. You have got a light source, a light coming from here. There is a G1, that is a plate here. It is a semi-silvered plate. So, the bottom is silvered, so that the light ray which is incident here, it will be partially reflected and travels along this direction. The other part will be transmitted and travel along this direction. And incident on mirror M1. M1, you see, it's a mirror. M2 is another mirror. So, M1, M2 are two mirrors kept perpendicular to each other. From the diagram, it is obvious that the two mirrors M1 and M2 are kept perpendicular to each other. You got a light source, then you got a glass plate kept at an angle of inclination 45 degrees. G1 is called a beam splitter. Why it is called beam splitter? The light beam is partially reflected and partially transmitted. So, partly it is reflected and partly it is transmitted. So, the light is split into two parts by the glass plate G1. That is the reason why it is called beam splitter. And G2 is known as a compensating plate. G2, I will tell you why it is called compensating plate later. So, G2 is another glass plate here kept at the same angle of inclination or parallel to G1. G2 will be parallel to G1, and the light coming here will be incident on the mirror M1, and there will be mirror M2. These two mirrors will be mutually perpendicular to each other, and the light rays which are reflected, there are the two plane mirrors. Light rays which are getting reflected from the mirrors M1, M2, you see the light rays coming back, they will interfere with each other, and whatever that you see after the interference occurs, whether you are going to have constructive interference or destructive interference, can be seen through the telescope or eye. You can have eye or telescope that is kept here. The same thing is shown here. Source is here. The beam splitter is the one that splits the light ray into transmitted mode and the transmitted mode and then the reflected mode. And so you have got one is a fixed mirror among the two mirrors M1, M2. One is fixed, the other can be moved either upward towards the direction of the beam splitter or away. It can be moved through lambda by 2 or 3 lambda. Anyway, it can be moved, right? You have got a micrometer screw, and this is called a compensator. It is called compensating plate G2. So you have got the fringes are observed here, something like what do you observe now? These fringes are similar to what you saw in the Newton's rings experiment. You see them, the sodium fringes, right? That is through the telescope, you can see them fringes observed. The two reflected rays which are coming from the mirrors M1, M2, okay, they will interfere with each other, and depending upon the condition under which the interference occurs, as I told you, as all of you will know, the interference will occur either constructively or destructively. Depending upon that, you will be getting bright rings or dark rings. So let me go back to the old slide. So depending on the difference between the distance between the two distances, right, the mirror M1 and M2, the two beams will interfere constructively or destructively. Plate G2 compensates for the thickness of G1, it is called compensator. At G1, the two waves are partially reflected and partially transmitted. As I told you, the G1 is a glass plate, it is a semi-silvered glass plate which will partially allow the light ray to go and be incident on one of the mirrors. Okay, then the part of the light ray will be reflected because semi-silvered is reflected, and will take this route and go to mirror, one of the mirrors here. The two mirrors are mutually perpendicular to each other, then they will be reflected back and the reflected rays will be interfering. And so a portion of the light ray is received, the receiver, or which may be a screen, a photo cell, or a human eye, or a telescope. You can have a screen. So at the end, what happens to the interference pattern? The nature of the interference pattern can be seen on the screen or by human eye, or you can have a detector like a photo cell. So this is what you have here, a eye or telescope or a photo cell. Okay, this is the experiment setup here. So depending upon the condition of the interference, you know the condition under which interference will occur, the brightness or darkness. So depending upon the condition, you will be getting bright or dark rings similar to Newton's experiment. Now we will go to summary part of the lecture 21. The refractive index of a liquid can be obtained by having the liquid between the glass plate and the lens and using the Newton's rings experiment. Haidinger fringes are obtained by having an extended source. An interferometer is an instrument in which two light beams interfere, giving rise to bright and dark fringes or rings which enable one to study the wavelength of the light source, the thickness of thin objects, and refractive indices of liquids and also gases. Construction, principle and working of Michelson Interferometer are explained. The questions are: how do you estimate the refractive index of a liquid using Newton's rings experiment? Explain Haidinger fringes. Question number 3. What is an interferometer? Mention its important applications, and the last question being describe the construction of Michelson's interferometer. With this we come to the end of the lecture 21, and the outcome of the Michelson interferometer and its varied applications will be seen in depth in the lectures to come. Thank you.